lesson, we're going to focus on properties of a couple special parallelograms. And essentially, we just want to learn what the properties are so that we can use them to actually solve a few problems. Now, running through them first, I'm putting this slide up right here so that people could write this one down. You can pause the video if you'd like to write it. Same thing with this next one. If you'd like to write them all down, you can pause them. But in general, we've got these pieces represented where everything that you're supposed to know today, I've got summarized on this one sheet. And for our people in class, I've also got this written on the marker board so that I'll reference it frequently throughout the lesson. People at home, you may want to pause the video, write these things down, so that way you'll have them when I reference them as well. Now, ultimately, what we're really focused on is understanding that last week we spent a boatload of time working with parallelograms. And we saw that because there were two sets of parallel sides, it forced a whole lot of things to wind up being true. Well, our focus right now is to look at a couple of other shapes. And the first one we're going to look at, of course, is a rectangle. What is the defining characteristic for a rectangle? Obviously, it's a quadrilateral, so it has four sides, but what's special about it? The feature that makes a rectangle special is actually that it's equiangular. All four of the angles have to be the same, and because they're all the same in a quadrilateral, it winds up meaning that all four of the angles will have to be 90 degrees. Because of the equiangular characteristic, it forces a whole lot of other things to be true. To start off with, it forces it to be a parallelogram. Anytime you have a rectangle, you know it's a parallelogram, and so we get all of the other things that we know are true. We know that it will have opposite sides that are parallel. Going back to elementary school, you probably should have remembered opposite sides of a rectangle are congruent. We also know opposite angles are congruent in a rectangle. We know that consecutive angles are supplementary. We know that the diagonals will bisect each other. We know that every rectangle is a parallelogram, so we get all of that information about parallelograms for free. There is one other piece that we get also. When we take a rectangle and we draw the two diagonals, they're not only going to cut each other in half, they're actually the same length also. We know with a general parallelogram, when you draw in the two diagonals, usually you're going to have a shorter diagonal and a longer diagonal. That won't happen with rectangles. With rectangles, they're the same length. And that's really all that we're talking about. The main things that you need to know about rectangles are that the diagonals will be the same and that it is a parallelogram, so we get all those parallelogram facts for free. The second shape that we're going to focus on, and let me grab this one. Instead of being equiangular, we've got the shape of a rhombus. And the defining characteristic for a rhombus is equilateral. All four of the sides have to be the same. Because these four sides are the same, it's going to force a lot of other things to be true. To start off with, it forces the shape to be a parallelogram. So once again, we get all of those parallelogram facts for free. We get the two pairs of opposite parallel sides. We get that opposite sides are congruent. Well, given that all four sides are the same, that one was obvious. We get opposite angles being congruent. We get consecutive angles being supplementary. We get that diagonals bisect each other, but because the four sides are also the same, we get a few extra facts. In particular, when we draw in the two diagonals, take a look at the angles we've got in the center. All four of those are going to be 90-degree angles. Because when you have a rhombus, the diagonals are going to be perpendicular to each other. They have to cross at 90s. Which is actually pretty interesting because since this is a parallelogram, we have to remember the diagonals bisect each other too. This left-hand side is the same as the right-hand side. Well, when we look at these two triangles then, we've got our 90s, matching hypotenuse, matching legs. These two triangles up on the top have to be congruent. Because they are congruent, we know those angles are congruent. Well, since the top and bottom part of the angles are the same, it tells us that this diagonal actually cut that angle into two smaller pieces. That's the last one. In a rhombus, the diagonals will bisect the angles. And of course, this happens on all four of, no matter how you draw it, you wind up with the same information. So these are the facts that you are expected to know. You are supposed to know that a rectangle gives you a parallelogram. It will have congruent diagonals. You are supposed to know that a rhombus will give you a parallelogram. The diagonals will be perpendicular, and the diagonals cut the angles in half. That's the information you're supposed to take away from it. It's the things that you're supposed to search for when you're working within a problem. And once again, all of that is summarized on this one page. So, what are we looking for? How are we going to get it? Obviously, take a look at the picture. Is this a rectangle or a rhombus? And if you couldn't recognize it just by looking at it, we're told right there, it's a rectangle. And so what we would observe, JK is 50, JL is 86. And we are searching for HM. How big is that piece? Here are a couple things that we would have to observe. It's a rectangle, so we know that the two diagonals are the same length. This other diagonal also has to be 86. But this is a parallelogram too. And in a parallelogram, the diagonals cut each other in half. So take the 86, cut it in half, and you get the bottom piece. Half of 86 is 43. Done. Taking advantage of the fact that we know the diagonals are congruent and that it is a parallelogram. Okay, here we've got a rhombus. What are we looking for? TV. Right? TV is over here on the right-hand side. Well, perhaps the most important characteristic to recognize here, it is a rhombus. And yes, we know that makes it a parallelogram and it gives us information about the diagonals, but we're not working with information about the diagonals. Don't forget that a rhombus is equilateral. All four sides are the same, and so we would be able to recognize pieces that are the same. We could create an equation for them. Recognizing that the top and the bottom have to be equal to each other. Well, here I'm going to subtract off 3b from both sides to get 10b. Then I'll add 9 to both sides and get 13. Dividing out by 10 tells us b is equal to 1.3. So taking that right back, 3 times b plus 4. 3 times 1.3 equals 3.9. 3.9 plus 4 gives us 7.9. which tells us then that all four sides of our rhombus have to be 7.9, and that's exactly what we were looking for. One side of the rhombus is 7.9. We're finished. Taking our next problem, of course, same picture, different goal. This one, we are searching for the measure of angle VTZ. So how big is that one? Once again, there are a whole lot of things that we need to recognize here. First of all, our center angles in a rhombus, they're all 90s. And because this is a 90-degree angle, we've got the ability to create an equation. 14a plus 20 has to be 90 due to our perpendiculars. We can subtract off 20 and get 14a equals 70. Dividing by 14 tells us a is equal to 5. Of course, is relevant because now we can come right up here and say this angle, 5 times 5 subtract 5, that's a 20-degree angle. And of course, that's not the angle we were looking for. That's angle XTZ. But we know that the diagonals cut an angle in half. So if the top half of the angle is 20, the bottom half also has to be 20 degrees. Because the diagonals bisect the angle. It gets chopped into two equal-sized pieces. Once again, we want to focus and say, we know what these characteristics are. There is also one other shape that we haven't examined yet. What if it's both equilateral and equiangular? That is, what if it's both a rectangle and at the same time it's a rhombus? Well, of course, we know that shape, a regular, then, is the square. Keep in mind, squares have a massive amount of properties because they're everything. They're rectangles, so we know that their diagonals are congruent. Squares are rhombuses, so we know that their diagonals are perpendicular. We know that their diagonals will bisect the angles. And because they're also parallelograms, we know that opposite sides are parallel. We know opposite angles are congruent. Opposite sides are congruent. Consecutive or supplementary. We know the diagonals bisect each other. We get all of those things about squares. And for this particular problem, we know that it's going to wind up being true, but this problem says, hey, crunch some numbers and actually show that this stuff works out. Show that the diagonals of a square are congruent. Show that they are perpendicular. And show that they are bisectors. So we're being asked for three things. Congruent diagonals, crunch numbers and actually get them. We need perpendicular diagonals, crunch numbers and get it. We need bisectors, crunch numbers and get it. And in order to do these things, we have a crap load of formulas that we need to rehash, ones that we've used before. We know that in order to get congruent, we need equal lengths or equal distances. So we are going to have to use the distance formula. And I'm not going to do this for both of them. I'm looking at the diagonal. Keep in mind that if we had S, T, V, W, and I know that this isn't drawn in the coordinate plane, but we would have the diagonal SV, and we would have the diagonal TW. Recognizing those ones, I'm looking at this and saying, I need to get the distance from S to V for this diagonal. Remember the distance formula. here. So we need to start plugging in and crunching some of our numbers using the points S and V. So there's S, here's V, and I'm circling them to make sure that I don't screw up and use different ones. We would have 6 subtract -5, and -3 subtract -4. So adding the opposite, we get 11 squared plus -3 plus 4 equals 1. So 1 squared, which is the square root of 121 plus 1. So we've got the square root of 122. That's our distance. In order to show that these diagonals are congruent, you will need to do the same process for the other diagonal, from T to W. And in an effort to save time with the video, we're not going to go through and crunch all those numbers. You've already demonstrated in your earlier units that this is a skill you have, so just remember that you plug in your stuff, you start crunching your numbers, and if you don't wind up with the same answer, then you've got a problem. Because you're being told, show that they're congruent, they have to be the same length, so if the numbers don't match, something went wrong. All of this stuff here with the blue would be to get just the one thing that they are congruent. Taking our second step, showing that they are perpendicular. Well, keep in mind, how do you know things are perpendicular in the plane? We know that they are perpendicular when they are opposite reciprocal slopes. And so to get this one, we're going to have to crunch the numbers, getting the slope of SV, getting the slope of TW. And so now we've got the task of where does slope come from? And I'm looking at this and saying I want to clear up some of the space because I don't want to have to bounce back and forth. Okay, so what was our slope formula? So once again, we've got the formula. We're just going to plug in the numbers. And so we would have, again, using S and V, 6 subtract -5, 3 subtract -4, gave us 11 over 1. There's our slope. In order to verify that they're actually perpendicular, you need to do the same thing with slope of TW using different points. And they need to be reciprocals, and they need to be opposites. If you don't wind up getting a slope of -1 over 11, if they're not opposite reciprocals, that lets you know something went wrong and that you need to fix it. All this stuff in the red would be used to show just that they are perpendicular. Which then brings us to our third piece, that they are bisectors. In order to get that they are bisectors, we have to know that they cut each other in half. They cut each other in half when they are connected to the midpoints. And so what you would need to do here is get the midpoint of SV. And so you need to use the midpoint formula, which we know there's our midpoint formula. So crunching those numbers, we'd have x plus x, y plus y, which gives us positive 1 over 2. Negative 3 plus negative 4 is negative 7, so negative 7 over 2, which is negative 3.5. Okay, those are the coordinates for the midpoint of SV. Those are the coordinates that actually cut the diagonal in half. To finish this problem, you would have to do the exact same thing for TW. And it would need to be the same midpoint. You get the same answer. That's how you would be able to go and get the fact that they are bisectors. And having gone over all this, here's what I can tell you that I'm absolutely certain. You're looking at it and saying, dear God, what the? Because that is a ton of work, isn't it?
Yeah, I know.
That is so much work that you just look at it and say, this is crazy. Why in the world would we want to do this? It's to prove a point with this one thing. When we're asked to get congruent, it's a lot of work. When we're asked to get perpendicular, it's a lot of work. When we're asked to get bisectors, it's a lot of work. Having spent a couple minutes trying to show 3 things only being true for one example, it was so much work that we're looking at it and saying, this is really, really hard. The advantage, though, is that we won't have to do those things because the theorems guarantee they are true. As long as you know that the facts are true, you would be able to simply say, I know that these things are equal because the theorem guarantees it. And you wouldn't have to go through all the extra work of showing that they are true for a specific problem when you know that they are true for every rectangle, for every square, for every rhombus. They work for all of them. And this stuff just saves, the theorems save you time from having to do things like this.